Um, there are many technical details as part of this, so I'm going to gloss over most of that, other than to try and give an idea sometimes of what method was used. Okay, so first of all, I should mention this was a paper written with my Wits University collaborators, Aubrey Bletcher. He and I still work together extensively. And in fact, in recent years, it's only been he and I are working most of the time, because Charlotte Brennan retired a few years ago and she decided she didn't want to do any more research. Aubrey is also retired, but luckily for me, has become a very enthusiastic researcher in his retirement. There's one other person who frequently worked with us in our Wits University group, and that is Margaret Archibald. Her name will appear a little bit later briefly. So let's move across and start talking about what all this is. Okay, so the picture is going to make things more clear, but just as an overall idea, the methods that are used in this paper, and in fact in probably most of the papers that I'm involved in, extensively we use generating functions to set up generating functions for counting whatever type of objects we are interested in. And then if we can, we try not to leave the answer just as a complicated generating function. We try, if possible, to extract the coefficients from the generating function, because that's the actual answer to the counting problem. And for that, one uses asymptotic methods and analytic tools. And I must say up front that when it comes to asymptotics and analytic tools, I owe a great debt to a former, also working in South Africa, professor, which was Professor Helmut Prodinger. He was at Stellenbosch, but I believe he retired maybe 3 to 5 years ago. But very much, he spent 6 years at Wits before he moved to Stellenbosch. And I must say, I, from him, grasped a lot of new methods in combinatorics that I certainly had not known before. So for the later portion of my career, in the last 20 years or so, I certainly owe him a big debt. Okay, so the next thing is this water idea can, in theory, have some applications. But this is the type of thing that you put in your paper only to try and sell it to the editor. So there's something about theoretical geomorphic structures. I can't even say exactly what that is. For me, the interest of the problem was that it's an interesting counting problem, and I really don't care less whether it's useful or not useful. So let's move across to the objects that we are going to study. So a Dyck path consists of up steps of the form 1, 1, and down steps of the form 1, -1 in the xy plane. And the condition is they must always stay above or on the x-axis. So in the picture shown there, I'm showing all the Dyck paths consisting of exactly 6 steps. And since the up and down steps are equal in number, it's most common to actually measure Dyck paths by the semi-length. So in that case, we would say these Dyck paths have semi-length 3. The number of Dyck paths is a very well-known quantity that comes up in combinatorics. It's counted by the Catalan numbers. As you can see, the Catalan numbers are rather simple. It's just 2n choose n times 1 over n plus 1. And also the Catalan numbers have a nice generating function, which involves a square root function of 1 minus 4z. Okay, so the basic idea is simple, and the idea should actually be credited originally to Aubrey Bletcher. In a vague sense, he said these individual dark paths, of which we are looking at 5 of them in the picture, look vaguely like the outline of a mountain range. And if you have a mountain, you can kind of imagine rain coming in from above, and the rain will pool itself in some of the valleys, and it will obviously run off from the parts that don't have valleys. So we move to the next slide, and now we see the picture in a nicer form. So in the left-hand picture, I've drawn a couple of dark paths, shaded in the inside of the dark path in green, maybe to give the impression of being a mountain. And then we've shown the water that accumulates if it falls from above, and any water that is not in some sort of valley is going to roll off and therefore disappear. So the question of interest, which was very appealing to me, was if we look at all the dark paths of semi-length n, of which we said there are a Catalan number of such paths, each of them has its own particular water capacity, which is can range from zero capacity for a very simple dark path that's just consisting of all up and all down, to other dark paths that have large numbers of little pools of water. So therefore, computing how much water is interesting, and in particular, we see that actually, if I turn the water upside down, as I've done in Figure 2, that the water itself is actually a dark path, except of course that it was upside down. So what that means is, if I want to find the area of the water, which is what we call the capacity, all I really need to do then is compute the area of the dark paths as given in Figure 2. Thereafter, we have to set up a whole lot of generating functions. So in particular, we have a generating function where z is marking the semi-length, in other words, the number of steps in the path, and x is marking the area that's making up the water. In other words, it's the area of those valleys. And something that is quite important for this is that if we go back to the water picture, you'll notice that the water is not allowed to be an arbitrary dark path, because if you look at the left-hand picture in Figure 1, then it should be clear that the height of the water, the upside-down height, if you like, certainly cannot be greater than the height of the entire dark path. So therefore, we are not interested in studying all dark paths. We are interested in studying dark paths with a parameter that we'll call h, which says that the dark path may not be more than h in size. And of course, h is going to vary. So first thing we need is a generating function for dark paths according to both their semi-length, which is the z variable, and according to their area, which is the x variable. But while this is not a difficult problem to do if you just consider all dark paths, it's a lot trickier if one wants to do only dark paths with a bounded height of h. And in that case, what we end up with is a quotient of two sums, each of which involves Q binomial coefficients. And for anyone who's not familiar with Q binomial coefficients, the definition is given towards the bottom of the slide. And we see that the Q binomial coefficients are themselves made up of products which run from I is naught to 1 less than the top index, which was n. What makes this problem tricky is that if you work with generating functions at all, you'll probably be well aware that if you have a two-variable generating function, such as we have here, and you want to find the total value with respect to one of the two variables, what you have to do is then differentiate the generating function with respect to that variable. In this case, that will be x. And after you've done that, you can put x as 1. Now, this is actually a more daunting task than one would initially like, because if you think about differentiating this quotient here, the first thing is that you have lots of Q binomial coefficients, and each Q binomial coefficient is a function of Q. In our case, we're going to replace Q by x squared, and therefore each product has to be differentiated with respect to x. This therefore means there's going to be extensive use of the ways to differentiate products, generalizations of the product rule. And we're also going to have to differentiate quotients eventually. So that's the quotient rule. And in addition, the formulas start to look quite nasty after a while. So then we turn to another nice idea, to which I should once again say thank you to Helmut Prodinger. And his nice idea was to use a change of variable, to move away from the x variable, which leads to very complicated generating functions, to a new variable called u, which makes the generating functions quite a lot more manageable. The next thing I should mention is that eventually we are going to want to evaluate these derivatives when x is 1. And the good news is when you get to the final step and you put x as 1, everything simplifies quite dramatically. For example, if we just take the ordinary Q binomial coefficient at the bottom there, n choose k with a q, and differentiate with respect to q, obviously you get a fairly complicated product. But after you put q as 1, the Q binomial coefficient basically simplifies to a binomial coefficient. And that's also true of the derivative of the Q binomial coefficient with respect to q. So eventually things start to look a lot nicer. Now the approach for doing this problem is to split up all these upside down water Dyck paths according to their height. And in particular, the highest part we will say has height r. That leads to that generating function phi r xz, which depends on the Q binomial coefficients. And after we've taken care of the middle, we can move left and right and look at water that is lower down in the path. And that leads to the product of phi h squared of xz. Again, if we look back at the picture, if you look in figure 1 at the right hand of the figure 1 pictures, you'll see we have a big water pool at the highest level. But then if we move to the left, there's a lower pool at a lower level. And potentially, if this was a more complicated Dyck path, we could also have more pools on the right-hand side. So this is the reason that we end up with a square of those functions. Okay, now after we've done all this work, we get a combined generating function of x and z. The details are fairly technical, and so for the purpose of this talk, I'm skipping over most of the technical stuff. Obviously, if anyone is interested in the paper, it's very easy to find the reprint online, or if that's a problem, to get it from me. And this is where we come to what I mentioned earlier. What we really need to do is take the complicated function cx comma z and differentiate with respect to the x variable, which will give the area of the water, and finally put x equal to 1. Now, I've always thought that I and my collaborators are fairly kind to the readers of our papers, in the sense that we tend to put in a fair amount of the working, because, as you know, in most areas of maths research, there's a tendency for people to leave out large chunks of their working, and the reader is therefore at the mercy of the author, because the author says, and step 2 simplifies after partial fractions to give you step 3. And without doing a considerable amount of work, you actually can't really verify that that is correct. So we were somewhat kinder to the audience, and put in a lot of the details of the calculation of this derivative. And while not anything particularly complicated, because after all, it's just differentiation, nevertheless, the details took a long time. And when I had a quick look back at my reprint of the paper, I saw that it was about 4 pages of work to actually show how to do all the differentiation in pretty much full detail. Maybe I've become lazier in my later days, because these days, as I mentioned, Charlotte Brennan has retired, and she was the person who did all the heavy lifting of typing up the papers. So now it's down to me and Aubrey mainly working together, and neither of us likes to do too much typing. So I think the newer papers lack the detail that these earlier papers had. Anyway, the point is, what you end up with is a function that depends on the square root of 1 minus 4z. And that's not surprising, because I mentioned that Dyck paths are related to the Catalan numbers. But a generating function that involves complicated products and quotients and sums of square roots is very intimidating, and not something that one could expect to be able to extract coefficients from. So this is where we use Helmut Proedinger's very clever idea, which is to say, replace the z variable in the complicated generating function by the u variable, where the connection between the z and the u variable is that z is equal to u divided by 1 plus u all squared. And the reason that we use that substitution is if we work it around the other way, then we see that u, in fact, has a square root built into it. And in particular, it's even the right square root for Catalan number purposes. So what that means is the square roots are hidden, and we end up with a rational function in u for our generating function. And here is a fairly compact version of what the generating function looks like in terms of the simpler u variable. So that's what's called equation 520. And even in the u variable, this is not something that one would consider to be very easy to manage, because the first thing we notice is that we in fact have a double sum over h and over r. And in addition, there's also some numerator factor xh, which I didn't print out. And that happens to just be a polynomial in U of degree 2h. So this is the simplified generating function, but nevertheless, it's not something that I would know how to extract coefficients from. The trick for this is to see if we can simplify the generating function. But before we do that, anytime one works in enumerative combinatorics, it's very important to check your generating functions as you go along, because it's very common to make mistakes along the way. And if you don't check, then you spend hours doing extra work on something that was already wrong. So therefore, step one is to go to equation 520, to replace the u by the original z variable, which is 521. And then with the help of computer algebra, which in my case is Mathematica, we do a series, and we try to check for the small cases that actually these coefficients are correct. So in particular, what we're going to do, we're going to take as our example 24z to the 4. So what does that mean? It means that if we look at all the Dyck paths of semi-length 4, of which there are 14 of them, because that happens to be the fourth Catalan number, if we add up the area of all the water, it should add up to 24. Okay, well, luckily that's a small enough case that we can actually check either by hand, or if we had the advantage, I think back in those days, of Charlotte doing the typing, and she also knew how to produce nice pictures, which is probably beyond what I could manage. So here she has drawn all the 14 Dyck paths of semi-length 4 and shaded in all the water capacity in blue. And as you can see, all of them have some water, except for the very last Dyck path, which doesn't. And if you actually add up all the areas, remembering that when you have a diagonal, you're getting half an area of a square. So we want our area to be the equivalent area of full squares. And indeed, this does work out to be 24. So the good news is the generating function looks like it's correct. Okay, now our aim is eventually to try and get ourselves either an exact or maybe also asymptotic formula for the total water capacity. And you can't really do that when you have a double sum. So the next part of the paper involves simplifying the double sum and converting it, again, after another page or two of work, into something that only involves single sums. So this, again, is fairly standard mathematics, but also lengthy to do. What you normally do with a double sum is you reverse the order of the sums. And having reversed the order of the sums, it's often the case that the inner sum either simplifies nicely or telescopes. And after doing that, one can end up with a single sum. So this is a much nicer formula for the total water capacity in terms of the U variable. As you can see now, the functions are a lot simpler. They do involve rational functions, but of a fairly simple type, like u to the r over 1 minus u to the r. And in fact, series of this type are actually given the name Lambert series.
The problem, of course, is that we actually want our answer eventually for the x variable, or rather, sorry, in terms of the actual original variable x, we don't want the answer in terms of u, because the u variable, it's not clear how that relates directly to the area. Okay, so I'm just going to give you a few brief viewpoints of part of the calculations without going into too many details. The first thing is that in order to simplify the generating function, as we have, you end up dealing with a lot of series that you would like to split up and make apart, and then shift indices and then combine with telescoping. And the first problem you encounter is a lot of these series are actually divergent. And our sums all run all the way from r is 1 or 2 to infinity. So therefore, the first thing you have to do is you have to fix a certain upper limit for your sum, which we'll call m, and do all our working for sums that have upper limit m. And the importance of that is, if we look, for example, at the very first sum in capital Vm of u, we see it's just the sum of the number 2. So potentially, this would be quite an illegitimate operation. I would be splitting up a divergent generating function and saying one of the terms is just the sum of 2, where in fact the sum runs all the way from 1 to infinity. Clearly, you can't do that. So the m upper bound is essential. Now, the next trick that we used is eventually, after you've done all the simplifying with your fixed m, we say, let's suppose we're only interested in the coefficients of the generating function that go up to u to the power m, and we don't care about anything that comes beyond that. Well, if that's the case, then I can replace capital Vmu by small m of u, and you'll notice that I have in the second line of capital Vm of u, there were some terms of the form u to the m plus 2, and you've noticed that I've just dropped those off. The reason being, if you're only going to do a Taylor expansion up to u to the m, then anything that comes out of u to the m plus 2 is not going to contribute. So therefore, I throw that away. And we are left with little Vmu, which is a rather simpler thing to do. And in particular, the important part, as the bottom line says, is that if we only go for coefficients that are with index less than or equal to m, the little Vm has the right coefficients. Okay, so now we go to the next page, and we can do some more combining of the simpler function. And the good news is that we can get rid of those divergent sums by combining them with some of the other sums. And eventually we get a little Vm, which simplifies quite nicely. And now we are finally back at the stage where we can say we don't want an upper bound m, we actually want infinity. But the good news is everything is now convergent, and we are allowed to let m tend to infinity. And this gives what I called the V infinity function. And the V infinity function is just multiplied by a fairly simple rational function at the bottom of the page to give the full derivative that we've been looking for. So the good news is this will give us our function in terms of u. And the next point is that now that we have a reasonably nice looking function, we can ask, is it possible to extract coefficients? And as you'll see, in particular, we have sums of the form u to the r over 1 minus u to the r summed over r. And as I mentioned before, those are called Lambert series. And it's fairly well known, especially in number theory, that we can expand Lambert series as ordinary power series using the divisor function from number theory. So with that in mind, we can actually get an exact formula for the total capacity of the Dyck paths of semi-length n, and the dr function is just the divisor function. So remember, divisor function is just counting how many divisors a number has. So for example, if the number is 6, then the divisors of 6 are 1, 2, 3, and 6, and there are 4 of them. Hence, D6 is 4, whereas in the case of 13, 13 is a prime number. It therefore only has 2 divisors. So in general, we have an answer in terms of the divisor function, and this is as simple as one can hope to get when dealing with such a complicated generating function. Now, the problem with exact answers is, while this looks fairly nice in some ways, it actually doesn't give you any intuition at all as to how large the water is as a function of the length n. It's very hard to look at this and say, what is the largest term that appears here? And clearly that's going to be a bit irregular because the divisor function can grow quite large for numbers like n factorial, but the divisor function always drops to 2 every time we get back to a prime number. So this exact formula is probably not a very nice way to try and get an asymptotic estimate. So for the asymptotic estimate, we go all the way back to the expansion with the Lambert series, with the u to the r over 1 minus u to the r. And now we have to do a whole lot of calculations on that generating function to eventually get what is the answer that we desire. And the answer that we finally get, which is what you would tell somebody who just wants to know what the result is. Basically, we end up with a total water capacity, which is some constant, which depends on pi, multiplied by the length of the path, or actually semi-length, which is n. And we see the water in fact grows like n to the power 3 over 2. So that's quite interesting. So the water is growing somewhere between n, which of course is just the length of the line. And if we had to take a full square, then we would have n squared as the area. So our water is somewhere intermediate of that. Now this last process involves using Mellon transforms and singularity analysis. So this is the analytic combinatorics part of the problem, which goes back to the main work in this area, which is the analytic combinatorics book written by Flagella and Sedgwick. And in particular, one uses Mellon transforms for a part of it. This is something that I definitely learned from Helmut Prodiger. And we also use some singularity analysis, which is both in the book and obviously Helmut knew that as well. So we're going to, I'm going to give you a brief outline of some of the details of doing the asymptotic expansion. Okay, so the first thing is we go back to our expression for the total capacity generating function, which is a function of u. And in some of the terms are simple enough that we can actually just substitute back what u is in terms of z. And after doing that, we actually find things cancel nicely. And in particular, the first term, which didn't involve a sigma, ends up just being a geometric series 1 over 2 into 1 minus 4z, from which we can immediately say the coefficients of that are just minus 4 to the n over 2. So that was actually very easy. Now we go to the second term in the generating function, and I've repeated it there so you can see it. So you see the second term has a rational function on the outside, but then it has one of these Lambert series on the inside. And the difference now is we want asymptotic estimates, which means we want to know how does this function behave near the singularity of the original z function. And if we look at the top line of the screen, we see that the square root has a dominant singularity when z equals 1/4, because that's when you have a 0 inside the square root. And z is 1/4 in terms of the u variable is actually mapped to the value u equals 1. So we want to find the behavior of this second term as u approaches 1. Okay, so some more substitutions come to the rescue. We set u equal to e to the minus t, and since we want u to tend to 1, it's enough to say let t tend to 0, because then obviously e to the minus t will tend to 1. We can therefore rewrite the first fraction in terms of t, and it's fairly easy, especially with the help of computer algebra, to do a series expansion for that. But the next part is we need to work out the sum r is 1 to infinity of u to the r over 1 minus u to the r. But you see that we've now rewritten this as a sum in terms of the t variable. And in terms of the t variable, this is not an elementary function, but there is a nice method for handling functions of this type, which is to use what's called the Mellon transform. The Mellon transform is just a common integral transform, similar in some ways to the Laplace transform, which is to say that we start with the function of t, we multiply by t to the s minus 1, and we integrate from 0 to infinity with respect to the t variable. And what results is going to be a function of the new variable s. So in this particular example, we end up with a function in terms of the s variable, which actually involves some well-known and very famous functions, namely capital gamma of s, that being the gamma function, and zeta squared of s, where zeta is the Riemann zeta function. But the good news is the behavior of these functions is something fairly well known. So what we have to do is, after we have this nice expression with gamma functions and zeta functions, is we want to revert to the t variable, and for that we have to use the inversion formula, which is again an integral, but this time it's a contour integral over a vertical line in the complex plane, which has real part 2. And the way to evaluate such integrals, as I eventually learned, was to make use of residues. If you remember any complex analysis, you'll know that residues is the way to work out a lot of contour integrals. The same applies here. And we get 7.3. Again, the computer taking a fair amount of credit for the work. Okay, we now combine 7.3 with the earlier expansion, multiply them together, to get 7.4. And that's very nice in the sense of we now have ourselves a reasonably nice answer, but it's an answer in terms of the t variable. We don't actually want the t variable. It's time for us to start unraveling everything and work backwards. So the first thing is, if I let the square root of 1 minus 4z be y, because that's definitely going to play a part because of the Catalan numbers, then e to the minus t, which is u, is also equal to 1 minus y over 1 plus y. And therefore, I can find the connection between t and y by solving e to the minus t equals 1 minus y over 1 plus y. And for asymptotic purposes, we don't need the whole answer. We are happy enough to see that t can be approximated by 2y plus 2y cubed over 3, plus higher terms that are not going to be important from the asymptotic point of view. So that means we rewrite our 7.4 in terms of the y variable, which gives what's at the bottom of the page. And finally, we go back to the original variable, which is the z variable, since y is just root of 1 minus 4z. And we end up with a function purely of z. And this is a function from which it is possible to extract coefficients. And the reason being that it's an asymptotic function, and we've dropped off all the really nasty parts of the generating function and only left the terms that make the greatest contribution to the growth of the coefficients. So the final step is to use what's called singularity analysis, which enables us to find the coefficient of z to the n in each of those terms one by one. And what we get is what's written in the middle line of this page. We see that our very first term involves minus log 1 minus 4z with a denominator 1 minus 4z. And that is well known to be a generating function for the harmonic numbers, which I write as hn, hn standing for the sum of 1 over k, k from 1 up to n. And on the other hand, I have also things like 1 over root 1 minus 4z. Well, it's easy to get coefficients from that if we just use the binomial series. In other words, we just end up with binomial coefficients like minus a half choose n, or a little bit later, like 1/2 choose n. So after doing the middle step, it's now a matter of Stirling's formula. Stirling's formula can replace each of the factorials in the binomial coefficients. And even better is that computer algebra can handle this kind of calculation, thank goodness. So with the help of the computer to do the work, we end up getting an expansion where the largest term is of the form 2 to the 2n times log n and gradually goes down. Okay, now this is not quite what we want, because there were 3 parts of my asymptotic expansion. I haven't shown you all the details. So what we have to do is we have to combine the 3 parts together after doing the work. And that gives the next equation. We notice that after we do the combination, we see we have some terms of the form 2 to the 2n, or if you prefer, 4 to the n. But there were some log terms that were there, and those have actually cancelled out. So those are gone, which is good. And now we can head to what we really want, which is what is the average capacity of a Dyck path? In other words, what is the mean value? And that means we must divide the top quantity, which is the total, by the total number of Dyck paths. Okay, again, a job for Stirling's formula or computer algebra. We want to know, as n tends to infinity, what is the behavior of 2n choose n times 1 over n plus 1. And we see that it's also something whose largest term involves 2 to the power 2n, which is good news because that means when I divide the one by the other, the 2 to the 2n will cancel out. But there are some further powers of n that come from the big bracket. And after doing the division, once again, the division is best done with Mathematica or Maple. We end up with the answer that I showed before and is repeated here in Theorem 3. So that brings us, I must just keep my eye on the time. Okay, so back to how does one do enumerative combinatorics? We have got ourselves an answer here after a considerable amount of work using both hand calculations and mathematical calculations. It's very easy to make mistakes, and in fact, it's very surprising if one doesn't. So very important is when you get an answer, you have to test it. If the test is no good, then you effectively have to start again or find the mistake. So for testing purposes, I took the value n equals 200. So 200 is not so large that you can't work out the exact answer from the generating function, but also big enough, we hope, so that the approximation in the asymptotic formula will be good, and we end up with 1268.88 from the asymptotic formula that we just got. And on the other hand, we can go back to the exact formula, which had the divisor function, work that out exactly, again with Mathematica, and what pops out is 1268.89. And this is indeed a very good batch. Usually, if your asymptotic and your exact formula are out by a small amount, like even 1 or 2, you would consider that to be good enough. So in this case, it was highly accurate, which is very reassuring. I should just make a point here, because somebody once mentioned to me, they said you only worked out the average. If you really want to study something properly, you also need to work out the variance and higher moments. And here's a good example of why working out only the average is not always a good idea. As you probably know, we have around 8 billion humans alive, and there are officially 8 planets in the solar system. So if we only go up by the average, then we can say that on average there are close to 1 billion people living on each planet of the solar system, which clearly it is correct as an average, but is obviously not meaningful. The good news is for the combinatorial problems we're doing, averages actually are usually pretty accurate, so that issue goes away. Now, in the last 5 minutes, I briefly want to talk about the water problem for other combinatorial objects. So in particular, here is a picture of what you can either consider to be a word or a composition. A word is just a list of numbers, and a word is represented by a vertical column of squares for each number. So if we look at the picture, we see that we have a first column height 3. 3 is followed by 1, followed by 2, followed by 5, followed by 2, and so on. And that list of numbers is what's called a word over the alphabet 1 up to 5. Alternatively, if we think of the orange thing as being one combined area, then if we sum up the area of all the orange squares, we actually get 42. And the sum of those numbers, 42, is the sum of 3 plus 1 plus 2 plus 5, etc. And that's called the composition of n. And as this picture shows, you can certainly pour water into words or into compositions and get water problems to study for that too. Here's yet another example where one can study water. And this was the paper that I did together with Margaret Archibald, who is also at Wits. This time we generate a word, but we generate a word by tossing a coin repeatedly. And we toss the coin and count how many times we toss it until heads turns up. So according to this picture, the first time I did this, I had to toss the coin 4 times to get a head. That's the first column. Then the next time I immediately got a head. That's why there's a column of height 1. The time after that, I threw tails, then heads. That's a column of height 2, and so on. And something of this form is called a geometric random word. And there's no, it's quite clear that if you represent the geometric random word also in this bar graph form, then again, you can ask what is the water capacity. So that we did. And now I very briefly want to mention Catalan words, because this happens to actually be the newest paper in the series. And I should actually point out that when we come up with a good idea, and Aubrey's idea of water, I thought was very nice. Water has also been studied by some other people like Tufik Mansour, who you might know if you work at all in enumerative combinatorics. So what is a Catalan word? Well, it's a word with an extra restriction. It's a word that has the property that you're not allowed to increase by more than one step as you move from left to right. So as you can see, there are some places where the word drops from height 5 down to 2. That's not a problem. Dropping is fine. But anytime we want to climb to a higher value, we have to have a staircase. So that's what we call a Catalan word. Here's another picture of the Catalan word. And without worrying about the details there, what's nice about Catalan words is that they are related to Dyck paths. Possibly a bit surprising, but actually there's a fairly straightforward bijection that converts a Catalan word into a Dyck path, or alternatively a Dyck path back to a Catalan word. Okay, there isn't really time to go through the bijection, but it's fairly simple. So the reason that's interesting is, together with Aubrey and Charlotte, we had written a paper about the water capacity of Dyck paths. So our first thought was, well, does that mean we can say something about the water capacity of Catalan words in view of the fact there's a bijection? The problem with that is that the bijection does not preserve the water capacity. So, for example, these 14 pictures here are in bijection with those 14 pictures there, which are Catalan words. But as you can see, there's virtually no water at all in the Catalan words. In fact, the only Catalan word that has any water is the middle one on the second row, which has 1 unit of water. All the rest have no water at all, because if you pour any water over them, it just runs off. So the good news is that working out the water for Catalan words is therefore a new problem, which means we could write another paper on it. And just to show what I was talking about, if we compare the water in Dyck paths with the water in Catalan words, then as our example showed, the coefficients in the generating function are very different numbers. Okay, now the first person to study water in Catalan words was actually Tufik Mansour and Mark Shattuck. And they did it by working with, they appeared to be perhaps unaware of this bijection with Dyck paths. So they didn't use Dyck paths at all. They worked directly with generating functions of words. And they got themselves a theorem, but a theorem which I consider to be totally impractical in terms of actual use. Because if you actually look at the theorem, you'll see that there's actually a multiple sum in the numerator and also a multiple sum in the denominator, which actually consists of m separate sums. And now suppose we wanted to work out, for example, back in our case where we have a word of length 200, it would be quite impossible even on the computer to work out a sum which involves 200 nested sigmas. So therefore this theorem is very interesting because it was tricky to get and is indeed exact, but it gives you no indication of what's going on. What I realized is that actually the water capacity of a Dyck path is connected to the water capacity of the Catalan word if we look at a certain subset of the water. And in particular, we see that the water capacity of the word from the top picture corresponds to the dark blue water in the lower picture. In other words, what I'm saying is, if we take all the water in the Dyck paths, I should only count the water that's above the up steps of the Dyck path, and I should also ignore any triangles that don't make up full squares. Okay, well, that's not too hard to do. We end up, again, using that generating function for Dyck paths of height h, but with some change of variables because of the fact that I've changed the definition of area. And after doing a very similar operation to what was done in the Dyck path paper, in other words, once again, we work with the u variable and we end up with this generating function for the total capacity of Catalan words, which I think is much, much nicer if you compare it with Mansour and Shattuck's formula, which had those nested sums. And of course, once you have this theorem, then the same methods as the previous paper can be used, first of all, to get an exact formula with divisors, and second of all, to get an asymptotic formula using Mellon transforms. And thank you. That brings me to the end of my talk.